Besides my home here on Earth, Mars is by far my favorite planet to visit. Whenever I'm leaving or returning to the system, if it's on the way, I make sure to slow down and appreciate the majesty of the red planet. Looking down upon its surface, it never ceases to amaze me how similar our two worlds are. Here is a second rock with signs of an atmosphere, geologic activity, river channels, and even huge deposits of water, together suggesting a time in the planet's history when these great volcanoes were still erupting. Water flowed through these channels and these ice caps were melted. And even though I thoroughly enjoy getting to see these awesome relics of Mars's more exciting past, it still always kind of bummed me out knowing that I'd never get to witness Mars during its prime, as after all, this is only a spaceship, not a time machine. But then I remembered I also have a time machine, so I put that in my spaceship, plugged in the space-time coordinates, sat back, and after just a few moments I'd arrived at my destination 4 billion years in the past, to a time when Mars had water. Okay, I know you all just want me to get to exploring right away, but if the purpose of this mission is to truly understand this time period, then we need to go back a little further to 4.5 billion years ago, the very beginning of Mars' story. This is when the planet first emerged as a primordial orb of molten rock from the cloud of debris orbiting the Sun, a time considered to be Mars' prehistory. It wouldn't be for another 400 million years before its surface cooled down enough to solidify, marking the first age in Mars' geologic history, the Noachian period. In this early state, Mars sported a thin rocky crust and a deep molten mantle, very similar to the Earth, giving rise to huge volcanoes that spilled vast quantities of magma out onto its surface. From this magma, gases such as carbon dioxide escaped and collected into a substantial atmospheric blanket around the planet. Although the giant shield volcanoes left behind, like Olympus Mons, are the most obvious evidence of this activity, it's the absolutely gargantuan platform they sit upon, known as the Tharsis Plateau, that reveals the true scale of volcanism that took place here. Spanning an area over 10,000 square kilometers and rising to an average elevation of 10 kilometers over the average planetary mean, or in other words, larger than the United States and taller than the Himalayas, the Tharsis is the largest volcanic structure in the solar system, containing over 300 million cubic kilometers of igneous rock. Based on our understanding of volcanic outgassing here on Earth, this volume of material would have released enough carbon dioxide to briefly build an atmosphere with the same or even greater pressure than we experience here. Though besides CO2, another byproduct of volcanic outgassing is water vapor, but as soon as this escaped the molten rock, instead of staying in the atmosphere, Mars's cold air would have caused most water vapor to immediately precipitate out, either as rain or possibly snow. Calculations, again based on Earth's magma, suggest that the building of the Tharsis platform could have released enough water to cover the entire planet in an ocean 120 meters deep. Though, of course, the Martian surface isn't perfectly flat, so as this water fell to the ground, it flowed downhill and collected into large water bodies. Now, I must admit there's no perfect representation of Mars during this time, as its climate was constantly fluctuating. During periods of reduced volcanic activity, its atmosphere would dwindle, global temperatures would fall below freezing, and ice would expand across the surface. But whenever volcanic activity increased, Mars's atmosphere would be replenished, allowing it to capture enough heat for the ice to thaw. Naturally, this melting would begin at its equator and extend towards the poles, going for however long the volcanic activity lasted. Fortunately, volcanism was abundant during the Noachian, and so there were long periods during which Mars was bathed in thick air and melted water. But to be honest, because we here on Earth in the year 2025 still don't quite know the full extent of this, I don't have an exact year to plug into my time machine to give us the best view of Mars's history. I guess I could have gone into the future and asked them about it, but instead I just visited a whole bunch of times and eventually stumbled upon this hotspot roughly 3.8 billion years ago that I'm calling the Noachian Maximum. During this, the warmest moment in the planet's lifetime, we can see bodies of liquid water extended further onto the surface than ever before, or ever since, covering nearly a third of its surface in an icy blue. Most of this was to be found in the northern hemisphere, within the Oceanus Borealis. Complete with rivers feeding into it, a circumpolar current, and polar ice in its northernmost regions, this truly earned the status of ocean. Beyond this northern water, however, Mars's southern highlands would have remained exceptionally dry. The one exception to this would be found down here in the Hellas Impact Basin. Located directly opposite or antipodal to the Tharsis region, this is the planet's deepest crater, and as such, any moisture carried south and deposited over these highlands would eventually find its way here, filling this up into the planet's second most substantial body of water. Exactly how full the lake was again depends on exactly what time we go back to, but satellite imagery suggests that at its fullest, the Hellas waters extended over 1.4 million square kilometers, over 4 times larger than the Caspian Sea here on Earth. As I mentioned earlier, within this crater is the deepest point on the planet's surface, meaning this would also harbor the deepest waters, far exceeding the depths found in the Borealis Ocean. This difference would even be visible from space, where the dark blue depths of Hellas contrast against the faint cold coastlines of the north. Directly above Hellas we'll find another impact feature, the Isidis crater. Here, the rim of the crater just barely overlaps with the northern basin, forming a nearly perfectly circular sea cutting into the Martian continent. Not only did this form a shallow, isolated cove, but this was also the southernmost extension of the Oceanus Borealis, bringing the body of water closer to the equator than anywhere else. That means the Isidis Sea would have held some of the warmest waters on the planet, making this another area of interest. The only other notable lake on the planet was further south within the Argyre crater. Though unlike Hellas, Argyre is exceedingly flat and not very deep, resulting in a much shallower body of water. In fact, at such latitudes, it's probable that for most of the planet's history, any water pouring into this crater would have frozen, leaving a great big puck of ice, with only its very deepest corner molten. Though at least very briefly during this Noachian maximum, conditions produced a third and final massive water body on the planet's surface, approximately the same size as the Caspian Sea. Of course, there would have been countless other smaller crater lakes as well, but in terms of the planet's overall hydrology, these three would have formed its most significant units, and overall illustrate how during the Noachian, Mars featured a fully functioning hydrological system. And this is something I feel like not enough people appreciate about this planet. For hundreds of millions of years, a collection of cold blue water bodies glistened upon its surface, marking the single most habitable era in Mars's entire history, a time when life itself might have even been possible here. Though whether or not life actually did take hold on Mars remains a mystery, one that not even my time machine can help answer. However, if we again look to Earth for a comparison, we'll find that at the same time oceans flowed on Mars, they were beginning to fill up the Earth's basins as well. Briefly, we can imagine Earth and Mars must have looked quite similar to one another, two freshly cooled planets both bursting with newborn volcanism and brimming with primordial oceans. And this is where my true interest lies, as the earliest traces for life on Earth come from about 3.8 billion years ago, with indications that it could have arisen even earlier. And considering the Noachian period lasted until 3.7 billion years ago, that means there was primitive life within Earth's primitive oceans at the same time Mars featured oceans of its own. And this naturally raises two big questions about life on Mars. First, if life developed on Earth in this amount of time, could the same have happened on Mars as well? Based on everything we know about the origins of life, the conditions necessary for it to arise were satisfied here, and so there's a real possibility life could have gotten started here. But even if it didn't, considering life was present on Earth, this raises the second big question. Could life from our planet ever have traveled to Mars? Although it seems unlikely at first, all it would really take is one single-celled organism successfully hitching a ride on debris from an asteroid collision to seed this entire ocean with life of Terran descent. And I don't know about you guys, but for me, the fact that two oceans of liquid water simultaneously existed in the same solar system and at least one had life in it, I don't know, it's honestly harder for me to believe they never cross-contaminated each other. That gives us two reasonable means by which life could have been present on Mars by about 3.8 billion years ago. Though either way, I think it's safe to say that if life was established here, the exact same rules of survival and evolution would apply. The very first forms of life on Earth were chemosynthetic, relying on chance encounters with complex molecules floating about in the water to sustain them. This meant that life only truly thrived near sources of high-energy compounds, such as hydrothermal vents, where fresh material from the core is constantly spewed out. As such, we have no other choice than to assume the same would have been true for whatever Martian life might have existed as well. What this means is that despite the planet's vast oceans, any life here would have been too primitive to properly utilize this space, and instead would have collected around vents on the ocean floor. This is what makes the search for life on Mars so difficult in modern times, as any vents that might have existed have since been buried beneath vast plains of sand. Besides deep-sea vents, the only other areas where all the ingredients for life would have been present is in the planet's shallows, where surface runoff regularly supplied new resources into the waters, though it's uncertain whether this could have sustained populations large enough to leave evidence of their existence behind. That's the unfortunate paradox of Noachian Mars. The planet was at its most habitable when life was still at its most basic, and these ideal conditions would only last another 100 million years before the volcanism started to wane, ushering in Mars's second geologic age, the Hesperian period. This era was defined by Mars's mantle progressively solidifying, leading to weaker and weaker volcanic phases followed by extended periods of dormancy. Naturally, this would have some major consequences on Martian life. For starters, one of the most direct effects of the planet's dying volcanism would be the cooling off of any hydrothermal vents. Being the one true source of energy for the primitive chemosynthetic Martians, this would immediately put all life on the planet at risk of extinction. However, eventually, even larger scale changes would begin taking place across the planet. Each time volcanism ceased, the atmosphere would diminish, trapping less of the sun's energy, causing global cooling. As the Martian air thinned, surface water both vaporized and froze, causing the oceans to recede as the planet effectively dried out. Together, the loss of volcanism would have made survival on a Hesperian Mars quite a challenge for even the most adapted of organisms. Though I believe it is still possible for life to have persisted during this time. Firstly, because asteroids continued colliding with the planet, breaking parts of the crust back open, releasing isolated pockets of volcanism all over the planet that could have acted as refuges for millions of years each. Periodically, however, enough pressure would build beneath the surface to break through and unleash brief ages of volcanism, warming the planet back up. Although these bouts were sporadic and often short-lived, they did occasionally return the planet to near Noachian conditions and would have provided respite for any life managing to cling on, only for the activity to inevitably die back down and the surface would freeze over once more. This oscillation between hot and cold was the defining feature of the Hesperian Age, extending the planet's potential habitability another 700 million years. Presenting even more mysteries in the story of life on Mars. How far could life have persisted into this period? And would it have followed on the same trajectory as life on Earth? If so, I'll remind you that it was about 3.4 billion years ago in the middle of the Hesperian that the very first photosynthetic life emerged within Earth's oceans. Although I find it unlikely for any native Martian life to have undergone the same evolutionary steps independently, once again it's possible for photosynthetic life to have been delivered to Mars from Earth. Whether or not this actually happened is again completely unknown, but even if we choose the optimistic path and imagine some photosynthetic life did arrive via space debris, it's still questionable if life could have established itself in an environment as harsh as this. The conditions of Hesperian Mars simply may have been too extreme for life to make the jump. But alright, even if we're super optimistic and trust photosynthetic life did find a way to inhabit some of the frozen Hesperian mud pits, from this point on the planet would only have another 400 million years before its crust would seal up completely, ushering Mars into its third and final geologic age, the Amazonian period. This time was characterized by a total solidifying of the planet's crust, and as a result, the complete vaporization of its atmosphere and the freeze-drying of its oceans. Even if both chemo and photosynthetic life had established itself here, it's doubtful any living thing could persist through these conditions. I mean, sure, maybe some life could still be buried deep underground, but it's safe to say life on the planet's surface was no longer feasible. And that's a real shame, because it wouldn't be for another billion years before multicellular life arose on Earth, and a billion years after that before anything even resembling intelligent life would emerge. So now that we've explored the timeline of Mars's humid period, we can see that even under the best of circumstances, life never could have crawled out of the proverbial cradle here, and the most we could ever expect to find are a few mats of organic matter lining the ocean floor. Although it's a disappointing conclusion, this newfound understanding does make the task of looking for evidence of life on Mars a little clearer, as we can begin to ponder where exactly we are most likely to find such deposits. Although it's hard to guess where exactly deep-sea vents might have arisen, there are some places that show evidence of water persisting long into the Hesperian. And if you're a longtime fan of this channel, you already know where I think we should look. Within the Great Hellas Crater, at its very base lies a series of cliffs, the Coronae Scopulus, which drop off into the lowest plain anywhere on the planet, the Peneus Palus. Being the absolute bottom of the planet, this would have been the first place to fill up with Noachian waters. And nearby valleys suggest water continued to flow here well into the Hesperian. But as Mars lost its atmosphere and its sea levels fell lower and lower, eventually only the very bottom of this basin had the air pressure and hydrology necessary to support one final body of water on the planet. Being the first and final Martian water body means this plane likely experienced the longest period of habitability out of anywhere on the planet's surface. Though even the bad water here would inevitably freeze dry away, once and for all, leaving the planet in the cold, barren state we find it in today. That being said, there are still a few places at the very nadir of this plain that show hints of hidden hydrology. Sites such as Badwater Crater and the nearby Hellas Chasma sit at elevations low enough and air pressures high enough to allow ice in the subsurface to melt. Where this occurs, the hypersaline meltwater flows downhill, creating these recurring flow lines on the planet's surface. While they don't look like much, these lines are the very last chapter in the fleeting story of liquid water on Mars, and although their chemical composition might not be ideal from an Earthling's perspective, this brine would likely be rich in dissolved compounds, not unlike the early Noachian waters, forcing me to ask, could there still be life here today? Was there ever life here to begin with? How far could it have evolved? Was this life related to me? And once I get my spacesuit repaired, where's the first place on Mars's surface I should go searching for evidence of this? These are the questions I always find myself asking every time I pass by. Alright, fine, you got me. No, I didn't really travel to Mars, I don't actually have a spaceship, and I still haven't figured out how to get my time machine up and running yet. So the only real tool I have to study the red planet with are the maps and images made available to me. And one map I found incredibly useful for this project was this one. I actually made this myself a few years ago by combining several different relief and surface maps into one, with the express purpose of illustrating the planet's topographic divide in an intuitive way, which I think I'd say I succeeded at. Originally, I hoped to use this all the way back in my Introduction to Areography video, so I had a copy printed, but I didn't end up going through with that, so instead this print has just been sitting on my set ever since. In that time, I'd like to believe this has become one of my most iconic set pieces. Though to be honest, I always felt a little bad about having this up here, as it sort of suggests this is a product that is available to buy somewhere. I can't tell you guys how many comments I've gotten asking where somebody can pick up a copy of this. So I finally decided to make this a reality and had a limited number of prints of this map made available to purchase up on my store, link in the description. Water on Mars is a subject we've been exploring on this channel since the very beginning, so there's really no map more emblematic of our studies than this. And yeah, I know this is a little soon after launching another poster earlier this year, but I've also had this on my set for over 3 years already, so if you ask me, this is long overdue. But now that I have a relationship with a printer, a business team, a warehouse, a website, and all that fun stuff, I'm finally playing catch up. So please, if you've ever admired this map from afar, or would like to explore this planet on your own, now's your opportunity to check out the link in the description and pick up one for yourself. Thank you all for watching, and I'll see you all again soon.